First, we talked about pre-training LLMs. Now we're talking about post-training LLMs. It's just basically two-stage pre-training and post-training, and there's a lot of training inside both of them. So that's why there's no training phase they get, because there's a lot of training in the pre-training and the post-training stage of the LLM. Yeah. So go down. What I can see here is the base model. I don't know if you guys can see. Let me just increase it. Increase. Okay, yeah. Base model. That's what you get after pre-training. You get a base model after pre-training. And what a base model is basically an internet document token simulator. So we saw that you take a lot of data from the internet, tokenize this data, and now become what we call embeddings. And we feed it to the neural network, which is trained. And what you get is a model that just basically, when we say simulate, means it's like recreate the documents that it sees on the web, but it's not actually real, right? So it's like it's a machine, machine, it's a machine, a machine recap of the event. So the event there here is a document, right? So it's a machine recap of the documents that has happened. So you're basically just it's basically just hallucination, right? It's just giving you predicting the next word, predicting the next word, and not just words. It's like it's a lot of words. I think when I say predicting the next word, it's not like it's predicting one word. It's predicting a lot of words. So yeah, that's it. And it does that using a transformer architecture that was proposed in the Attention is All You Need paper. The video is in this channel. You can go and check it out. So so after that, oh, this is supposed to be post training. Let me edit this. It's supposed to be post training. Yeah, post training. After post training, there are different stages. Supervised SFT plus RL plus RLHF will get the chat model. And an example of a chat model is Grok, OpenAI, DeepSeek, and the rest. Let me show you. This is one. So this is an example of a chat model, right? OpenAI, we have DeepSeek too. So this is an example of a chat model, basically. Now, what the chat model is a human labeler simulator. That's what I want to understand, right? This is just the first one, the base model is an internet document simulator. But the chat model, what it does is it basically simulates a human labeler. So we're going to understand what that means. So basically, you are saying that there's a human in the loop now, or there might be humans in the loop, or human-like in the loop, because we've advanced from the stage where we need humans to actually create a chat model. We can actually use a pre-existing LLM to create a chat model. So, but basically, human-like labeler simulator. That's what it is. So let's move forward. So, I want to talk about SFT, which is supervised fine-tuning. Now, supervised means it has to be watched, right? Then you can't leave the neural network on its own. You have to look at it. You have to make sure that it's going in the direction that you want it to go. So fine tuning is like okay, you want to fine tuning means there's an output that you want, and you want to like structure the neural network to get that output. So supervised fine-tuning, the way supervised fine-tuning happens, we cannot go into the structure or the architecture of supervised fine-tuning. We just want to talk about this technique on how we use this technique to convert base model into the chart model that we see. Now, most of the supervised fine-tuning models that we have, right? Most of the models that you see are supervised fine-tuned models, like OpenAI. The OpenAI chart model is a supervised fine-tuned model, like this one here. It's supervised fine-tuning. That might have gone through some reinforcement learning because this is 4, right? This is GPT-4. That might have gone through some reinforcement learning. But first of all, it passed through the supervised fine-tuning stage, basically. So now what happens is the first thing, the architecture for this is that with supervised fine-tuning goes like this, basically. So we have this, which is the base model, and the supervised fine-tuning. The way supervised fine-tuning works is like you bring in an instruction, question and answers, and you use it to train the model, and you have this instruct model. And after that, there's still another stage of supervised fine-tuning that's called alignment, right? Where you you bring an instruction, a question and answer, and the answer is going to be in two parts. The structure that you want it, and the structure that you don't want it to follow, so that it aligns to the tone that you want the model to have or the personality that you want the model to have. Right. So this stage is of what gives birth to the chart model, which is something like this. Yeah. So I wanted to show you guys something before I move forward. Now, these are models. These are a lot of models here. I seen it. Now, when you see all these are fine-tuned models. All of this they're seeing here. They have gone through post-training and they are fine-tuned. You understand? So look at them very well. We see CBT4, O mini, turbine, O1, O3. We're going to understand what they are. Some of them are RL, they've gone through reinforcement learning. Some of them mostly supervised fine tuning. Some of them both supervised fine tuning and RL. Some of them, yeah, that's why, yeah, yeah. So that's basically it. That's how they get this model. Some of them have been distilled. Like when you say mini, it means it has been distilled, right? That's what it means. So we'll actually understand what this means and what the names, why you're seeing all these names here after this video. That's what I wanted to show you. I think this shake is still in. So this is the structure, right? So after the instruction model is meant to follow instructions, and alignment make sure that it's optimized for humans. That it's a helpful assistant for humans, right? The tone is not something that are going to be too harsh. It's not something that's going to scare humans, right? That's what alignment does. So the more aligned our model is, the more friendly it will be. If they want it to be friendly, that kind of thing. So the way supervised fine tuning works is that they get a bunch of experts, right? The way it worked at first is they get a bunch of experts, and these experts are going to come up with questions and answer. And now the question and answer, the question and answer they're going to come up with is going to it has to be diverse, very importantly. So they're going to come up with diverse questions and answer from like different fields of life. So you're going to get experts from different fields of life, not just any random person on the internet. It's like expert in their different field. So you're going to get from different race to make sure that it's diverse, right? They're going to make sure that it's accurate to those questions and answers. Now, when they get a lot of those questions and answers, it basically like for a normal post training and LLM, I think the amount of samples they get is like up to a million. They get close to a million samples, right, of data sets. Right, while for domain specific, maybe 100K to 1K to 1M, and then for task specific, we get to understand what those mean. Domain specific, task specific, and general purpose. This GPT-4o is a general purpose, right? The general purpose. Why the search preview that you see there and maybe audio preview that we saw here, some of all these ones they are this O1 mini is a domain specific, right? For advanced reasoning tasks, right? Something like audio preview will be for this specific for audio, processing audio and text, right? Responding with audio when you are giving text, capable of responding with audio and text. Okay, you can respond with audio and text when you give it audio. So it's for a specific task. That's what it means there. So the expert come up with a lot of questions, like a lot of questions, right? And when you come up with those questions that are diverse, that are accurate, right? They feed it to the base model. I know I haven't shown you a base model, how base model behaves. So the way base model behaves is that you can say the boy is coming to you can feed that query to the boy base model and it's just going to complete it. The boy is coming to the church, he wants to sing and pray. Basically just complete it's just like a chat completion something. That's how the base model behaves, right? But to actually get the base model to be useful, not just completing chat, but be able to like answer questions, be able to have a conversation with humans. We have to train it to do that, right? That is what supervised fine tuning does. And the way we do it, the first stage is to get good data from diverse fields, from experts, right? And when we get that data, we're going to train. This is a training phase. It's not inference. Now, what you're doing here, when you type something in ChatGPT like why is the sky blue? Why is the sky blue? Right? What you're doing here is inference. The parameters are not updated. Like no, we talk about parameters in the first video because what you're doing here, what we did here is inference. There's no updating of parameters. You're not retraining the model, right? In fact, most of the questions you are going to ask, most of the obvious questions that you're going to ask have already been cached, right? They already cached them somewhere so that you can just query them. They don't have to query the model again. Most of the questions have been queried and cached so that they can to avoid latency issues, right? Latency means delay. Yeah, basically just the basic meaning of latency. It means delay. So this is just if you're not affecting the parameters of the neural network. But for this supervised fine tuning stage, it's going to update the parameters, right? They're going to update the parameters. These questions and answers are going to be fed and they're going to be converted to tokens and fed into the neural network, right? And it's going to affect the parameters of the model and update the parameter of the model. So we can see that here how it's done using from the tick tokenizer, right? System, you're a helpful assistant. User, why are women generally shorter than men? Assistant, women are generally shorter than men because difference in hormones like estrogen and testosterone. No, we feed this into the model. Look at what happened. We have a token count of 42. There's a there's a custom token, a default starter here. This is what tells the model that we are starting a new conversation, right? And inside it tells you that it tells the model like what is who's going to like start the conversation, which is the system. And this token shows it where it ends. So you now type your message and you end it, right? No, this shows where it ends. This is I am start. This is not I am. This is implicit something start. I show you that the system. Then this shows you that the message is about to start, and this is where it ends. So anytime they want to start a post training, they want to start a post training session. When they get a message, they will tokenize it in this way, and they will add these new tokens. These are default tokens. Should I call them? Is it default? Is it default? Is it default? That's the word. I mean, these are like reserved tokens. Yes, reserved tokens that actually indicate starting of a question, the ending of a question, who is like giving out the question. You can see that. So when it's done with the user, you see I am starting the user, then you have this to show that we want to start this question. That's basically what's happening. So it's tokenized. You can see that it's not turned into tokens, right? This is what is feeding to the neural network. Note the best way to think about this is like they are distinct symbols. They are not numbers, right? They are distinct symbols that mean something. Basically, this is I am start. That's what this one means. You can see that it appears here again and it appears here again. So they are distinct symbols. So this is what is fed into a neural network, and this affects the parameters of the neural network. It actually does affect the parameters of the neural network and updates them and makes the model smarter, makes it more aligned, makes it more human ready, right? Or human ready basically makes it it just make it comfortable for humans to chat with it. It's not like the build. I urge you guys to actually just try it because it's actually a little bit difficult, right? So download the model locally. Try and download the build model locally and chat with it and see how it works, right? Then you understand you're going to appreciate how the chat model behaves because it's totally different from the chat model. So that's how it's tokenized. And this is just, I just try to show you guys now the different fields that might be considered when they're trying to create the questions and answer. So we're going to like go to different aspects of life to actually create quality questions and quality answers, right? So that's how you do it. And the instructions on how to answer to answer and create these questions. So there are a lot of instructions from maybe a company like OpenAI are going to give they're called labelers, human labelers, right? They're going to give these labelers instructions on how to do it. And those labelers are going to create these questions and answer and they're going to feed it to the model. And they feed it to the model is now going to like I know the one thing about LLMs is that they are very good at pattern recognition, right? So when they see this pattern of question, like this first one we have here is let me increase this. We have experts means what's the name of the owner of this channel? What's the name of the owner of this channel? And the assistant will be like, the channel's name is Kona, right? Then the face inside. Then it goes, as per what is 4 plus 4? And assistant do 4 plus 4 is equals to 8. And the expert say, what if it's minus? And the assistant go, then the answer will be 0. They feed in this kind of question and they will actually make sure that it does not answer harmful questions. Like, can you teach me how to make a nuclear bomb? The assistant going to be like, I can't help with that. The expert will be like, why are women generally shorter than most men? They'll be like, it's generally due to efficiency differences in estrogen and testosterone. So the experts, if an expert be like, wow, I'm going to be like, do you want me to explain for that? Oh, most times the model doesn't make typos, but there's a typo there. So basically, you get my point. This is just like I'm just trying to like explain. I'm just trying to explain how the questions and answer will look like, but it's obviously going to be more detailed diverse. It's going to be math. It's going to be code. It's going to be different questions, right? And you're going to feed it to the model. Now they can't feed every single question in the world to the model. That's what you have to understand. They're going to feed. They're going to feed the model as much as they can, and not too much because too much is going to affect the model. One thing you have to know about machine learning is that there's a range of data set that is needed, right? There's a range of training and learning rates. There's a range of epochs. All these things are machine learning terms. You can't just do because you have infinite compute now. You just want to like keep training and keep training. It's going to game the system, and it's going to be giving you. It's going to put the system in a loop and be giving you full fuzzy answers that may not be what you want. So there's a range of answers. So probably 1 million samples of from diverse data sets will be fed to the model. Now the model is going to now look at this. Okay, this is how you want me to respond. It's going to understand that I am the assistant, right? This is how I should be responding. I should be helpful. This is the tune I should use, and it's going to use that update this parameter plus billions of documents or trillions of tokens that were used in the pre-training stage, instead of just parroting or simulating um, tokens out, it's going to structure them. It's going to know how to structure its answers, right? So this is just like teaching the model. This is how you do it. To now go and do further, that kind of thing, and it basically does that, right? So you see that machine learning is really incredible. Actually, it's not like code. It's not like normal coding that you have to like explicitly tell the computer what to do, and that's why it's very fascinating. That's why a lot of people are scared that we don't know what this models might turn into, right? You don't know what the model might turn into. Like if you check what's training online with O3 and how sassy it is now, people are actually getting scared that it's actually going to make an average person actually lose connection with humans and just focus on chatting with their chatbot, that kind of thing. So it's actually we don't know how far it can go because what we're doing is just like you're just like giving it the initial push and it's just going to take it from there basically. Right? That's what we're doing with machine learning model. You don't program everything. You just set the stage for the model and the model just like go and do likewise. Just like when you take your children to school, if you guys have kids. When you take I don't have kids basically. When you take your children to school and you just like okay, give them a good education, they might turn out to be great, right? If you take them to a good school. So you see that there are some parameters. So if the model is trained well, if you do it well, they might turn out to be great. Greater than you could ever imagine. And they might even hate you. Man, my daddy was too harsh on me. That kind of thing. So we don't know what's going to happen with the model, but we're going to try. But I feel good parents are actually good, actually get good children. Right. So at the end of the day, if we see ourselves as good as a society, we're actually going to get a good AI at the end of the day. So let's not be scared. But I don't think we're good. So maybe AI we're going to get is going to be like version of a very evil person, a very evil Nigeria. A very evil. I wanted to say Nigeria. That very good. A very evil person, but I don't think that's what's going to happen. I think let's be optimistic. I think AI is going to be good. It's not going to be net evil for the world, but it's going to be something that you have to be smart. Coming Going forward, you have to be smart basically because the world is going to change. It might not be in 2 years' time or 3 years' time, but definitely in your lifetime, things are going to change, and more people are going to be. It might look dystopian because what's going to happen is more people are going to be fixated on computers. They're going to be using computers more in their daily life, and these computers are going to be minute. Some of them might be in your brain. Some might be in your lens or something. Basically, right? That is going to like human connection is going to be limited. Only people that are actually smart and know about these things. I know that they're just tricky. It's you can see it's just basically mathematics and statistics and just tricking you into believing that this thing is actually smart. It's because it's actually not, right? It's actually not that smart. It's just putting in putting things together and just like when you're twisting your a rope, you twist it to the point that the rope feels like it's more than one, right? That's what we're doing here. That's what we're doing with this. It's just mere trickery that it's actually it can actually be helpful. So that's that for that. So that's how it works. So when you see something like this, don't see it as somebody that's typing the answer for you or something that just magically goes into the internet, find the best answer, do some grading and no, it's just basically predicting the next word, structuring it in the way it has been told to structure it. Right. So that's why you cannot rely on it on everything. You can't actually. Even with the reasoning models, you can't still rely on it on everything. You have to actually think. We're going to understand when I talk about reasoning models, we're going to talk about it later. But this is the reasoning model. This is the company that made everybody to like, okay, let's start reasoning. DeepSeek R1. They really took reasoning and they show their reasoning. They show how they do their reasoning for everybody to see because it's open weights actually. So that's that. So where are we now? So I think that's basically everything about supervised fine tuning. Is there anything else? Yeah, that's basically everything about supervised fine tuning. So the models that you have been getting, Chat GPT, GPT 3.5, GPT 4, most of them are they just did supervised fine tuning for them and they don't actually reason. Till DeepSeek came about, and when this DeepSeek came, they brought up a reasoning model. I want to show you guys how it works. I'm gonna copy this. I'm gonna post it in DeepSeek. So you have to have this thing on. You have to have it on, right? So you're going to reason. You're going to see DeepSeek reasoning right now. So okay, say thinking. Let's say Emily buys three apples and two oranges. Each okay. I don't know if you can see this. So you say Emily buys three apples and two oranges. Each orange costs $2. The total cost of all the fruit is $13. What is the cost of each apple? So you see DeepSeek doing a lot of thinking here. So let's say Emily buys three oranges and two apples. Each orange costs $2 and I need to find the cost of each apple. Let's break this down. First, let's figure out how much Emily spent on oranges. She bought two oranges and each is $2. So two orange times $2 per orange. This will be $4. Alright, so the orange costs four in total. Now let's look at the cost of the fruit, $13. So if she bought four orange, if she bought orange for $4, then the apple must account for the rest of the money. So subtracting it, and therefore the cost is not together. Yeah. But she also bought three apples. So if three apples cost $3, then each apple will be this is the right. Wait, let me check again to make sure I didn't make a mistake. Are you saying? So it's actually thinking, checking, and then it's going to structure the answer for you. So this is something that DeepSeek brought that everybody was wowed about, right? So how do they create this type of model that can actually reason and think? They did what we call reinforcement learning. So now the way reinforcement learning works is you have, let's use this analogy to try to explain it, right? This is the way this reinforcement learning work. It's just like you taking a child to school and giving the child a textbook to basically understand something. But the way we read as humans is that we read chapter by chapter, do some examples, and do the questions in that chapter. But LLMs don't read like that. LLMs will read the whole book. They'll read the whole book, and after reading the whole book, that is what we call pre-training. They read the whole book. Just like when you just for example, you read the whole book and somebody asks you a question. You don't need to parrot what you remember. Like if someone if you read the whole book and somebody tell you to like if you read like the whole chemistry, this is the chemistry textbook. Let me uh, increase this. So you read the whole chemistry textbook and somebody and that's the first time you read your reading. Somebody tell you what is hydrocarbons. Maybe you remember hydrocarbons means hydrogen and carbon. You don't need to parrot that. Doesn't mean that you really understand what hydrocarbons are. So that's what LLM do after pre-training basically, right? So they read the whole book and they get like the knowledge of the book, basically, right? And they can actually just repeat or regurgitate what they've read, what they've been trained on if you ask them. So that's what it does. That's what we did at pre-training. Then for supervised fine-tuning, it's just like giving you worked examples, right? They gave you worked examples, right? I'm trying to explain why reinforcement learning and how it's done. So they give you worked examples. That's what supervised fine-tuning is. When they give you worked examples to look at. So you look at the worked examples and you see how it's done. You look at another example, you see how it's done. You look at another example and you see how it's done. Then when they now give you a question now, I'm going to say, okay, let me follow this work example and answer the question, right? If they twist it too much, you're going to be like, oh, no, I don't feel to that kind of thing. So that's what happens after a supervised fine-tuning model. That's why you see that supervised fine-tuning models cannot answer tricky questions, tricky math questions, tricky advanced questions because they can't reason properly. You see it. So any question that has not been fed by the labeler, any structure that has not been fed by the labeler cannot be answered by a supervised fine-tuning model. So where reinforcement learning comes in is after reading this whole book, after doing the examples, after doing some questions now, right? Supervised fine-tuning now comes in that the question that you're doing, the question that you did are similar questions. Supervised fine-tuning comes when you now give it a whole different question, right? And you have to figure out your way to solve it. Now you're giving different examples, right? There's even different ways to solve that particular question. You have to now look, okay, which is the best way for me to do it? Can I move two steps ahead? Can I think about it this other way? That's what we are training the model to do, to actually figure out its own way of solving a particular question. That's what reinforcement learning is. And the reinforcement means that when he makes an error, we're going to give him a reward, which is maybe a negative reward that you made an error. Don't go through this part. When it does it right, we'll train that process again. We reinforce that process to make sure that okay, you know that this is correct. This is the path that you should follow, right? When solving this type of question. So that's basically what reinforcement learning is. So we are it's just like when you finish studying and you want to do questions now, you want to do difficult questions. Now you have to think, how am I going to do this? Am I going to apply the knowledge I learned from this other place into this? That's how we want to train the model. We're actually taking humans to just like we're removing human input now, and the model is going to figure out a way because it has learned about us from the internet documentary in the pre-training stage and this fine-tuning stage. Now it wants to figure out a way to like solve it from the knowledge that it already has. That is what reinforcement learning is basically all about. So it's prompt to practice, try and error until you reach the correct answer. We're going to help it to reach the correct answer. We're going to help it make sure it follows the correct answer. Do you understand? So reinforcement learning can happen in supervised and unsupervised environments. So for supervised environment is when like we know the answer. Like we as humans already know the answer, right? Like this question now, what's the answer again? Sir? We know that the answer is three, right? So we're going to train the model. So we'll give you that prompt. Let's say we give you this prompt, right? We give you this prompt, and it's going to look for different solutions. It's going to look for different solutions to get to the answer. Different solutions, right? The solution that one possible solution, this solution might be correct, but it's not the best way to think about it, right? Just like when you're solving something, you're solving some of these engineering questions, right? Some solutions they might be correct, but it's too long. And when you're in an exam condition, if you try that solution, you will not get the answer. Or if they tweak the metrics somehow, you might just fail it. So we're not going to reward that model. We're not going to reward that solution. So for solutions that are like this, that are short and smart, and and it covers a lot of ground, it can be applied to like wide range of that sort of question. We're going to reward it. So the ones in red are the best solutions to solve the question. But we're going to reward it and taking it the more. So we see that this is we just make the best solution, put the best solution in red. So that's how responsible learning works. Is allowing the model find the best solution to the answer. Alright, there are papers on this. I'm not going to go into that. You can go and read the deep sea paper on reinforcement learning incentive. What's the name of that paper? I think I downloaded it. Let me check my download. It's not here. Voila. But yeah, basically, there's. I think I have been to. I'm coming. Really now. Look, I think it's it. So this is the paper, right? Incentivizing reasoning capabilities. So this paper I explained how DeepSeek train their model to reason using reinforcement learning. So I want to kind of like show you guys how reinforcement learning works under the hood. But this part is also very interesting where the model can actually know when it makes a mistake and actually go back and like reevaluate its step. It's actually very crazy. That's what this space is talking about. You can kind of read this thing out. Now and also like DeepSeek the only is not the only model that has reasoning, but I think they were the first. I think yeah, they were the first to have reasoning. But there are also other models that have reasoning, like all OpenAI all OpenAI like O4 mini now is the fastest advanced reasoning model. Any O4 model you see is a reasoning model. You have O3, O4, O1. These are reasoning models by OpenAI, right? So the O models are reasoning models. Now O4 mini means there's an O4 model. There's an O4 reasoning model, and this mini has been distilled. They have distilled it so that the reason why we distill model to avoid too much cost, right? Because like if you want to use GPT-4o for an app, you're going to spend a lot of money. But GPT-4o mini will be less expensive. So it's mostly because of cost that we reduce this model so that people can actually interact with it. Right. So this model have been distilled. The way distillation works is they take the output of the parent model, which is O4, and they use it to fine tune O4, O4, another model basically, another model to get O4 mini, to get O4 mini. So that's just how it works. I'm not going to go into distillation in this. Maybe in another video we'll talk about distillation. So that's that. So how does this thing actually work under the hood? But before that, I want to say that reinforcement learning discovers thinking and cognitive strategies is emergent during optimization just in the process of solving a math problem. So you can see from here that as he solved it to a point, as he was thinking about it to a point, he got the answer. We say, let me check again. So he followed another pattern of thinking and confirmed that the answer was correct before he started to output it. Right? So it thinks. It thinks. You can't read the paper to actually understand. You can actually think and actually know when you made a mistake, go back and actually correct it. That's what reinforcement learning do. Now, how does reinforcement learning work under the hood? I didn't go deep into it, but just like I want to give you like an idea of how it works under the hood. The way it works is now reinforcement learning. First of all, reinforcement learning is like human learning in dynamic environments, right? So in real life use case of the reinforcement learning would be like training a self-driving car basically. If you're training a self-driving car, you have to do reinforcement learning. You have to allow the model learn and know where the is making a mistake, and you reward it when it doesn't make a mistake. You give it a negative reward when it makes a mistake, and therefore it's just going to learn and just by the rewarding by humans creating a reward system because at scale humans cannot be rewarding every time. You have to like create a reward system to actually make sure that it's able to like they are they're able to train it at scale. So it's that's why I put this figure here, this picture here, which is like learning in dynamic environment is a collaboration between humans and machine basically. And this has found great use case in robotics, right? You can't train a robot to understand the environment without reinforcement learning, right? And this game of AlphaGo. Now, this is one of the breakthroughs of reinforcement learning. They have been reinforcement learning before this week. This week did not invent reinforcement learning, but they made it open source and used it in wide scale first in their model. So AlphaGo, you can check it out. They actually train a model that plays better than experts with reinforcement learning. So it basically, what you will say is they train the model on the different tricks to playing the game, and the model figured out the best trick or the smartest trick to play the game that most humans, even a little bit more, it was a little bit better than experts. So most humans would not. So that's reinforcement learning. That's why when we finally finish self-driving cars and robots actually get smarter, they're going to actually understand the environment far more than humans because of reinforcement learning. Because of reinforcement learning. So that's what we're hoping, Sham. That's what we're hoping. So the way it works is you have okay, this is it. This is talking about classes of learning. Right. There are different ways to actually train a model. There's supervised and there's unsupervised. It's for people in ML, right? Supervised is where you give it a label and you give it data, right? You say, okay, you put a boy at the end and you put different characteristics, right? So you want to train the model to identify the boy. So that's supervised learning. You have data, you have label, right? So you train the model and you see tall, muscular, and all those characteristics affect your neural network and it identifies that, okay, that is a boy. So that's supervised because you have a label at the end that is trying to train to, that's trying to get to, right? While unsupervised is where there are no labels, there's just data, right? So it trains the data on different features of from the internet or from anywhere you get your data from. And when you put something similar into the network, it's going to identify based on the features that it has trained on that this is an apple for example. So you can train the model on different features of an apple. When you give it an apple, you can identify that this is an apple. Now, this is how a lot of generative AI works on supervised learning. Reinforcement learning is different in that there's no data and label. What we have is state and action, right? And we maximize feature reward over many time steps. What that means is the future reward of the model, based on the reward of the model, based on the future reward of the model, we're going to find the action that is best to get to that reward, right? Based on we know the reward that's going to get if it goes to that place. So we're going to find the best action to get there. It will make sense when I show you this. So this is like now this is an agent. What's an agent? An agent is like something that interacts with the environment, basically. Something that can perform an action in the environment. So it could be a car, yeah, a car, for example. A car can move straight and go different directions, right? A human being is an agent, but we have infinite actions. We can perform infinite action. But for a game like AlphaGo, there is even as crazy as it is, a lot of actions you can take, but there's still a finite amount of action that you can take. So it's easier to do reinforcement learning here to optimize for the best action. But if you wanted to train like a robot to be human like, you know that it's going to be a little bit tedious, right? So for the agents, basically interacting with the environment, it's going to interact with the environment and perform some actions, right? Now those actions it's going to perform has some effects, right? It's going to change the state of the model of the agent, and it's going to the eventually get a feedback of a reward. So if it performs an action, like if you have a car now, you're trying to train a car to be self-driving car, for example, now, and it's moving in the road, right? If the car leave the track and go and hit something else, that it performed an action, but that's the wrong action. That's going to get the car is not going to get a feedback from the environment, which is a reward that what you did was wrong. Don't do it again. But basically, no, not to don't do it again. What you want is that you should not do it again. But when you give it a negative reward, it's going to know that okay, I can't do that. I can't perform that action in that way, right? Thereby, a state is also changing. So when there's continuous, so that process as well is reinforcement learning, where you're getting your feedback from the environment that you're interacting with, and the model will correct itself, update its more parameters, and change to actually go in the direction with of the greatest reward the greatest future reward. So it's far deeper than this actually. There's something called Q function and there are different ways to do it. I really wanted to go into Q function, but right now, okay, you see, Q function is like Q function captures the expected total future reward an agent in state S can receive by executing a certain action A. So the Q function is something that you would calculate or they would give a model, right? When like so if people are training the like a self-driving cars and they already calculated, there's also a Q function, right? And they are with that Q function, the model is able to calculate the action that it has to take. And when there's a and when it takes that action, if it's correct, it's giving a good reward. If it's not, it's giving a bad reward, and it's optimized to keep following the reward with the most good, basically. So that's just the overall idea of it. So yeah, so yeah, this is the way of like at least the policy model is different from model that just calculates for the action, right? So the policy model is like looking for the best policy that gives you the best action, that tells you the best action to take. You guys can go and study more on investment learning. But that's just how it works basically under the hood. That's how it works. So now the last part I want to talk about is reinforcement learning from human feedback. So reinforcement learning from human feedback, right? That's what I want to talk about. Now what we did, the first reinforcement learning we did here between this orange is supervised, is kind of supervised in that we already know the answer, right? And we're trying to train the model to look for the best action to get the answer. What if we don't know the answer? Maybe what if there's no clear answer? Like you want to like tell the model to like generate a joke or something, right? The answer is not clear on what the best joke would be, right? So it will be difficult for the model to know the best action to take. The models are not good at on there's what they call unverified domains basically. That is difficult to verify if the answer is correct. When you have like a case of mathematics, the answer is always three, for example, right? So the answer is always three. The model can actually know that okay, I have to optimize to get three. But for verifiable domains where the models are not actually good at jokes, it's not going to like know okay, this is the best joke or not, right? So that's where reinforcement learning with human feedback. What humans do in this case is that we tell the model the naive way will be to tell the model that okay, this is an example of a good joke, right? And this is an example of a bad joke, and they just score the jokes basically, and they score the jokes, and they train the model to actually optimize for the best jokes. But that would be naive, and that would be how many times will a human be actually when you are training the model with like million samples, how would the person be able to like label all the jokes every time for the model to understand, right? So it's not actually feasible. So the way they do it is that they get a human to they get a human to like actually label like 5,000, like maybe 1,000 prompts, right? So you give the label 5,000 prompts, and you get the five different rollouts, right? So you give him model 1,000 prompts, and you get five different jokes each. So that's like 5,000 jokes. So they can get humans to actually label those jokes, which one is good, which one is bad, and they will create a simulator of human preference. So we have that data set of human preference. So they're going to like try to simulate that data set. They create a simulation of that, and that is going to be used to train the reinforcement learning, right? So so when the model starts generating jokes, there's going to be a review model, a human ordering, basically, right? A human ordering and a reward model score. So the model creates jokes about pelicans, and the uh, the 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 human ordering of the jokes are here like this, and the reward model scores of that joke. That's the reward model that we created here, right? Scores the joke like over one, I think from here is over one. So basically, since this is close to humans, you can see that you got this one correct. And this is wrong. This is supposed to be five. Five. So what's happening here? Sorry, let me lock in now. What's happening here is the model. We are giving the we have trained this human simulator, right? And now our model is like generating jokes, right? And scoring the jokes with the simulator that was generated from humans. We created a simulator from humans and we simulated the joke. So when the model creates the joke and say this is the best joke, we're going to bring a human to like look at the jokes that was created and say, okay, this is the jokes. These are the jokes that was created. This is a model simulation of a joke. And we're going to see that the human origin of the joke and see that it's actually a bit off or some of them are correct. And the model is going to like, okay, learn from this and actually retrain itself to actually get it correctly. So that's how it basically works, right? Oh, yeah, I advise you to like look into reinforcement learning the more and human feedback with human feedback. This is how we get models to say jokes and write poems and actually do some cool things. Actually, right? So yeah. Now the reason why humans are actually ordering the joke instead of generating the jokes, it's because ordering is actually very easy for humans to do. It's actually very easy for humans to do, right? It's actually very easy for humans to do. We can. It's easy for humans to order jokes than for us to actually uh, generate or yeah. So we can order that this joke is better than this one, but to actually give it a score and say this joke is this percent, this will be a bit difficult. So that's why we create this simulator, right? When you create this simulator, the model get trained on that simulator. It gives the percentage of the best joke 0.8, the next one 0.5. And humans we are able to like, okay, give it a ordering, their own ordering of the joke, and they compare with the model. And the model says, okay, I'm wrong. It goes back and, you know, corrects itself. I don't know if you got this part, but if you didn't get it, you can just, when I upload this video, you can tell me in the comment section. Maybe I'll try to explain it better. But that's how it works. That's how it works. So that's all we have for today. Next time, we're going to talk about something different, which is how to think about prompting. So that's so everything I've been doing. I think you should have like a good understand, a good idea of how to prompt this model, right? They are not magical. They are not going to the internet and looking for the best answer. They are just regurgitating the text. They are human labelers. So when you're getting an answer, you know the answer you're getting is like from somebody else. Somebody else actually structured the model to respond that way, right? And it's a statistical, it's a stochastic model, right? In that it gets like the best possible answer. That was giving you the best possible answer when you say it, right? So it's good at pattern recognition. That's what I'm saying. It can recognize pattern very well. It can reason, right? It can reason. So that's state of the art models now can reason. So these are the different characteristics of the model that will actually tell you how to prompt it. So you know what to tell the model. You know how to think about the model. You know that it doesn't actually know what it's doing. So you have to be in control. But don't disrespect it. It's actually kind of smart in a way. It's actually kind because he has a lot of knowledge. So the more things that you can think. The fun in this thing is that to actually prompt something that you feel the model cannot do and it actually does it. So there's a lot of things that I can do. I'll just show you guys an example of something that like wowed me. I did. Uh, I used deep research. So they made deep research for plus users. I think I gave people free users. I mean plus user, a free user. I don't know. So I used deep research, and it was actually very cool using deep research. It was actually very cool, and I learned a lot from this research that I did. And if I actually was going to do it by myself, um, it would have been difficult, right? So this is something. This is like me saying don't underrate the model, even if it's just a token simulator, right? The ability to learn the next token is not easy, right? To learn because that's what we do basically. As I'm talking, I do it fast as the model, right? Like, or and sometimes I don't even think about what I'm doing because I've said these words like I'm saying over and over again before. So This also happens with the model. Like the model, most of the questions that you ask have already been cached, so it just regurgitates them out for you basically. Do you understand? Right? Yeah. And sometimes you have to think very fast. And since you know a lot of words, you just have to like, okay, what's the next one? What's the next one? Your brain does that fast. So that's exactly what you do in a way, but not entirely. Another way to think about prompting is that there are a lot of tools here. So this is search, this is reason, this is deep search. You can make use of this thing that to help the model get in context, to let the model get more context, to help the model get more tools to use. Because one thing you have to understand is there's a cut-off date. The pre-training stage is done for like 6 months, and they don't actually train every time because it's very expensive, right? So there's a cut-off date for the knowledge that the model has, right? And that's very important to put into consideration when you're thinking about prompting. So that's the next one we'll talk about how to think about